Imagine standing on the bank of a concrete channel in the middle of the Panamanian jungle, watching a cargo ship the length of 3 football fields float toward a pair of steel doors 7 stories tall. Those doors weigh more than 600 tons each, and in a few minutes they are going to swing open, let the ship inside, seal shut behind it, and then the water is going to rise, quietly. No pumps, no engines forcing it upward, just gravity, pulling water from a lake 85 feet above sea level down through tunnels cut into the concrete floor. The ship will rise with it, lifted like a bathtub toy, until it is sitting at the elevation of the mountaintops. This is the Panama Canal lock system, and the fact that it works at all is one of the most absurd achievements in engineering history. The problem started with geography. North America and South America are connected by a narrow strip of land called the Isthmus of Panama. It is only about 50 miles wide at its thinnest point, but running down the middle of it, like a wall, is the Continental Divide, a ridge of mountains and volcanic rock that separates the Atlantic watershed from the Pacific. For centuries, that ridge turned the Americas into a wall between 2 oceans. Any ship sailing from New York to San Francisco had to go all the way down around Cape Horn at the southern tip of South America. That is a voyage of roughly 13,000 miles through some of the most dangerous waters on the planet. Storms in the Drake Passage sank ships regularly. The journey took weeks, and every mile of it was unnecessary if someone could just punch a hole through Panama. The Spanish talked about doing it as far back as the 1500s. King Charles V of Spain actually ordered a survey of possible canal routes in 1534. But the jungle, the mountains, and the sheer ambition of the idea kept it as a fantasy for the next 300 years. It was not until the 1800s that anyone seriously tried, and when they did, the result was one of the worst disasters in the history of civil engineering. The man behind the first real attempt was a Frenchman named Ferdinand de Lesseps, and on paper, he was the perfect candidate. De Lesseps had just pulled off one of the greatest construction projects of the 19th century. He had built the Suez Canal in Egypt, a sea-level waterway connecting the Mediterranean to the Red Sea. The Suez opened in 1869, and it made de Lesseps a celebrity across Europe. Investors loved him. The French public treated him like a hero. So when he stood up in front of a Congress of Engineers in Paris in 1879 and announced that he was going to do the same thing in Panama, people cheered. They threw money at the project. 800,000 French citizens bought shares in his canal company. The initial cost estimate came in at 1.2 billion francs. It felt like a sure thing. But de Lesseps made a critical error before a single shovel touched Panamanian soil. He insisted on building a sea-level canal, the same approach that worked in Egypt. The logic seemed sound. You dig a trench from one ocean to the other, fill it with water, and ships sail straight through. No locks, no gates, no lifting mechanism, just a flat channel. The problem was that Egypt is flat desert. Panama is not. Panama is a wall of volcanic rock and clay covered in jungle, soaked in tropical rain, and infested with mosquitoes carrying yellow fever and malaria. The Continental Divide in the canal zone sits 85 feet above sea level. To build a sea-level canal, de Lesseps would have had to dig through that mountain ridge all the way down to the ocean floor. The volume of earth that needed to be removed was staggering, and the rock was not cooperative. It was a mix of hard basalt and soft clay that collapsed in landslides every time the workers thought they had made progress. Entire sections of excavation would fill back in overnight. But the real killer was not the rock. It was disease. In the 1880s, nobody understood that mosquitoes transmitted yellow fever and malaria. The French workers lived in barracks surrounded by standing water. They kept flowers in pots on their windowsills, and the saucers underneath those pots became breeding pools for the Aedes aegypti mosquito, the species that carries yellow fever. Workers would feel fine in the morning and be dead by nightfall. At the peak of the French construction, roughly 200 men were dying every month from disease alone. The hospitals were so overwhelmed that the legs of patient beds were placed in small cups of water to keep ants from crawling up. Those cups of water bred more mosquitoes. The very measures meant to help were accelerating the epidemic. By 1889, the French project had consumed 1.5 billion francs. Over 22,000 workers were dead. Only 11 miles of the 45-mile canal had been dug, and most of that digging was nowhere near deep enough. The company declared bankruptcy. De Lesseps and his son Charles were charged with fraud. 800,000 French investors lost everything. The whole affair became known as the Panama Scandal, and it nearly brought down the French government. De Lesseps, the hero of Suez, died in disgrace in 1894 at the age of 89. That could have been the end of the story. The canal could have stayed a half-dug ditch in the jungle forever, but the United States had been watching. In 1903, the US backed Panamanian independence from Colombia and quickly signed a treaty giving America control of a 10-mile-wide strip across the isthmus. The following year, the United States formally took over the failed French canal project. They bought the French company's equipment, its excavation, and what was left of its infrastructure. The price was $40 million for a project that had already swallowed the equivalent of $11 billion in today's money. The first American chief engineer was John Frank Stevens, a railroad man from the Midwest who had never built a canal before. But Stevens understood something that de Lesseps never accepted. He understood that you do not fight the mountain, you go over it. Stevens looked at the geography and made the decision that saved the entire project. He threw out the sea-level canal design and proposed a lock canal instead. Rather than digging all the way down to sea level through the Continental Divide, he would dam the Chagres River to create a massive artificial lake 85 feet above sea level. Ships would enter the canal at the ocean, get lifted up to the lake through a series of water-filled chambers called locks, sail across the lake, and then get lowered back down to the ocean on the other side. The mountain would not be removed, it would be floated over. This was not a popular decision at first. A lot of people in Washington wanted the sea-level canal. It felt simpler, more elegant. President Theodore Roosevelt himself had to weigh in before Congress approved the lock design. Roosevelt had made the canal a centerpiece of his presidency. In November 1906, he traveled to Panama to inspect the work personally, making him the first sitting American president to leave the country on official business. Photographs from the visit show Roosevelt sitting at the controls of a 95-ton Bucyrus steam shovel, grinning in a white suit covered in mud. He came back to Washington, convinced that Stevens was right. A sea-level canal would have taken at least 18 years and required removing roughly 200 million cubic yards of additional rock. The lock canal could be finished in 8 years and would use the existing terrain as an advantage rather than fighting it. But before a single yard of concrete could be poured for the locks, someone had to solve the problem that had destroyed the French. And that someone was an army surgeon from Alabama named William Gorgas. Gorgas arrived in Panama in 1904 as the chief sanitary officer. He already knew what the French had not. Thanks to the work of Cuban epidemiologist Carlos Finlay and US Army doctor Walter Reed, scientists had confirmed that mosquitoes transmitted yellow fever. Gorgas had already used this knowledge to wipe out yellow fever in Havana, Cuba, after the Spanish-American War. Now, he deployed the same strategy across the entire canal zone. He launched one of the largest sanitation campaigns in history. More than 4,000 workers were organized into mosquito brigades that fanned out across the isthmus. They drained every pond, swamp, and puddle they could find. They poured kerosene oil over standing water that could not be drained, suffocating mosquito larvae before they could hatch. They cut grass below 12 inches across the entire zone. They installed screens on windows and doors. They fumigated buildings. They sprayed custom poisons across breeding grounds. It was brutal, exhausting, unglamorous work, and it saved the entire project. By 1906, yellow fever had been completely eradicated from the canal zone. Malaria never disappeared entirely, but Gorgas drove the death rate down to a fraction of what the French had suffered. Without Gorgas, the American effort would have ended the same way the French one did. He did not design a lock or pour a yard of concrete, but the canal could not have been built without him. With the disease problem under control, construction kicked into a scale that is hard to imagine today. In 1907, Stevens resigned and was replaced by Army Colonel George Washington Goethals, who would see the project through to completion. Goethals ran the canal zone like a military operation because, in many ways, that is exactly what it was. The most grueling task was carving the Culebra Cut, later renamed the Gatun Cut, through the Continental Divide. This was a 9-mile stretch where the canal had to pass directly through the mountain ridge. The man in charge was Major David Gaillard, and the job nearly broke him. Workers blasted and drilled through volcanic rock in temperatures above 100 degrees Fahrenheit, with tropical rain dumping over 11 inches per month during the wet season. 102 Bucyrus steam shovels, manufactured in South Milwaukee, Wisconsin, each weighing up to 95 tons, chewed into the hillside 10 hours a day, 6 days a week. Each shovel could scoop up 5 cubic yards of rock and clay in a single bite. Dynamite crews drilled holes into the rock face, packed them with explosives, and blew entire hillsides apart before the shovels moved in. The canal consumed every pound of dynamite produced in the United States, along with all of the country's cement output and most of its structural steel. By the time the cut was finished, crews had excavated roughly 96 million cubic yards of earth and rock from that stretch alone. To put that number in perspective, you could fill a freight train long enough to wrap around the equator, but the rock fought back. The geology in the Culebra Cut was unstable. Layers of soft clay sat beneath harder rock, and the weight of the hillsides pushing inward caused massive landslides that poured millions of cubic yards of material right back into the excavation. The notorious Cucaracha slide kept filling in sections of the cut for years. Workers would spend weeks clearing a section only to arrive one morning and find it completely buried again. There were moments when the floor of the excavation itself rose up, pushed skyward by the pressure of the surrounding hills. While the Culebra Cut was being blasted through, a second massive project was underway at the Atlantic entrance. Gatun Dam, built across the Chagres River, was designed to create the lake that the entire lock system depended on. When completed, it was the largest earthen dam in the world, stretching 1.5 miles across the valley and standing 105 feet tall. Behind it, the Chagres River backed up and flooded 164 square miles of jungle, creating Gatun Lake, which was at the time the largest artificial body of water ever made. The lake would provide the water to operate every lock on both sides of the canal, all of it flowing by gravity. Now the centerpiece, the locks themselves, 3 sets in total. Gatun. Locks on the Atlantic side, with 3 chambers stacked in a row to lift ships 85 feet from the ocean up to the lake. Pedro Miguel locks on the Pacific side, with a single chamber dropping ships 31 feet. And Miraflores locks, a few miles further toward the Pacific, with 2 chambers lowering ships the remaining 54 feet back down to sea level. Each lock chamber measured 1,000 feet long and 110 feet wide. To build them, workers poured over 3.4 million cubic meters of concrete across all 3 sites. The Gatun locks alone consumed more than 2 million cubic yards of concrete, making them the largest concrete structure on the planet at that time. Nothing comparable would be built until the Hoover Dam 2 decades later. Overhead cableways strung between 85-foot steel towers carried 6-ton buckets of wet concrete from mixing plants to the construction site. Electric railways hauled stone, sand, and cement to the mixers. The operation ran continuously. At Gatun, more than 4.5 million cubic yards of material had to be excavated before a single form was set. Workers reached the final floor level and then removed another 186,000 cubic yards of material by hand. But the concrete was only the container. The real engineering miracle was the gates. The lock gates are the moving parts that make the entire system work. They are what separate one chamber from the next, holding back millions of gallons of water while a ship sits inside waiting to be raised or lowered. And designing them was considered the single most difficult technical challenge of the entire project. George Washington Goethals himself said that the canal could not have been built without the man who designed those gates, an Army officer named Lieutenant Colonel Harry Hodges. Hodges had no established model to work from. Nobody had ever built anything like this before. The gates had to swing easily enough to open and close in 2 minutes, yet they also had to withstand the enormous pressure of water pressing against them. A contradiction in engineering terms. They had to be massive enough to block a chamber 110 feet wide, yet precise enough to seal watertight every single time. And they had to last for decades without failing, because a single gate failure could drain an entire lock, damage any ship inside, and shut down half the canal. What Hodges came up with was brilliant. Each gate consists of 2 leaves, like a pair of double doors. Each leaf is 65 feet wide and 7 feet thick. The height varies depending on location, from 47 feet at the shallowest locks up to 82 feet at the lower Miraflores chamber, where Pacific tidal swings add extra height requirements. The tallest gates stand as high as an 8-story building. Here is where it gets clever. The gates are hollow, built as a series of watertight compartments, like the hull of a ship. When the lock chamber fills with water, the submerged portion of each gate becomes buoyant. The gate floats in the water, which dramatically reduces the load on its hinges. A solid steel wall that tall would rip any hinge ever made right out of the concrete. But a hollow, buoyant gate barely weighs anything at all once the water is up. The heaviest gate leaves weigh 662 tons. The hinges that support them each weigh about 37,000 pounds. Even so, the buoyancy is so effective that just 2 electric motors, each producing only 25 horsepower, are enough to swing an entire gate leaf open or closed. 25 horsepower, that is roughly the output of a riding lawnmower, and it moves a 600-ton steel wall. The operating mechanism was designed by Edward Schildhauer, an electrical engineer from Wisconsin who had no blueprint to follow. Schildhauer created a system where each gate leaf connects through a steel arm called a strut to a massive bull wheel embedded in the lock wall. Each bull wheel is 20 feet in diameter and lies flat, like a horizontal gear. The electric motor turns the bull wheel, and the strut pushes or pulls the gate leaf in an arc, exactly the way a connecting rod on a steam locomotive turns a driving wheel. If one motor fails, the other can still operate the gate alone. Redundancy was built into every component because there was no room for failure. The gates close in a V shape, with the point of the V facing upstream toward the higher water. This is called a mitre gate design, and it is self-sealing. The pressure of the water on the upstream side pushes the 2 leaves together at the point of the V, locking them more tightly the more pressure is applied. The water itself holds the gate shut. No mechanical latch is needed. The harder the water pushes, the stronger the seal becomes. Building these gates was one of the most dangerous jobs in the canal zone. As many as 165 rivet gangs, made up mostly of West Indian laborers, worked simultaneously driving rivets into the steel plates that formed the gate walls. Over the course of construction, they drove more than 6 million rivets into the 46 gates across all 3 lock sites. At the peak of production, workers were hammering 660,000 rivets per month. The riveting crews worked on rickety scaffolding high above the lock floor, and there was always the risk of scaffolding giving way, either their own or the one above them. Once the locks and gates were built, ships still needed a way to stay centered inside the narrow chambers. The solution was a fleet of small electric locomotives that ran on tracks along the top of the lock walls. These were called mules, named after the pack animals that had traditionally hauled boats through smaller canals. The original fleet of 40 mules was built by General Electric in Schenectady, New York in 1914. Each mule attached a steel cable to the ship and used a rack and pinion gear system to move along the wall at walking speed, keeping the vessel perfectly aligned as it entered and exited each chamber. A large ship required up to 8 mules, 2 on each side at the bow and 2 on each side at the stern. The mules did not pull the ship forward. The ship moved under its own engine power. The mules provided side-to-side control and braking, keeping the vessel from touching the chamber walls, where even a minor collision could crack the concrete or damage the gate mechanisms. The lock chambers fill with water through a system of culverts, large tunnels cut into the floors and walls of each chamber. These culverts connect to the higher water source, either Gatun Lake or the chamber above. When valves open, water flows downhill by gravity, filling the chamber from below. No pumps are involved anywhere in the system. Every drop of water that lifts a ship through the Panama Canal is moved by gravity alone. A single lockage uses roughly 52 million gallons of fresh water drawn from Gatun Lake. The chamber fills in about 8 minutes, and the ship inside rises with it, smooth and steady, like an elevator with no moving parts besides the water itself. Think about what is actually happening during a transit. A cargo ship approaches the Gatun locks from the Caribbean. It pulls alongside the guide wall, and mules attach steel cables to the bow and stern. The first set of gates opens. The ship eases forward into the chamber under its own power, and the gates close behind it. Valves open in the culverts below. Water from the chamber ahead, which sits at a higher level, floods in through the floor. The ship begins to rise. In 8 minutes, it has climbed about 28 feet. The gates ahead open, and the ship moves into the next chamber. The process repeats. 3 chambers, 3 lifts, and the ship is sitting on Gatun Lake, 85 feet above where it started. From there, it sails across the lake and through the Culebra Cut under open sky. Then it descends through Pedro Miguel and Miraflores, lowered step by step back to the Pacific. The entire operation, all of it controlled from a single control tower perched on the center wall of each lock, with one operator directing over 1,000 electric motors. Before the canal could officially open, the locks had to be tested. On September 26, 1913, the tugboat Gatun became the first vessel to pass through the Gatun locks. The gates swung, the water rose. The system worked exactly as Hodges and Schildhauer had designed it. 2 weeks later, on October 10th, President Woodrow Wilson sat at a telegraph machine in the White House and pressed a button. That signal triggered the detonation of the Gamboa Dike, the last barrier separating the Culebra Cut from Gatun Lake. Water rushed in, connecting the Atlantic and Pacific channels for the first time. The canal was complete. Plans were made for a massive celebration. A fleet of international warships was supposed to assemble and sail through the canal to San Francisco for a world exposition. But World War I had broken out in Europe just days earlier, in August 1914, and the grand opening was quietly cancelled. Instead, on August 15, 1914, a modest ceremony took place as the American steamship SS Ancon entered the Gatun locks under the guidance of canal pilot Captain John Constantine. Colonel Goethals watched from a railcar on the bank as the ship rose through the 3 chambers, crossed Gatun Lake, passed through the Culebra Cut, and descended through Pedro Miguel and Miraflores to the Pacific. The transit took about 9 hours. The most expensive construction project in American history up to that point, costing roughly $375 million, equivalent to more than $8 billion today, was open for business. The total human cost was staggering. About 5,600 workers died during the American construction phase from accidents and disease. Combined with the estimated 22,000 deaths during the French attempt, roughly 27,500 people gave their lives to connect 2 oceans across 50 miles of jungle and rock. But what they built has endured. The original lock gates, the ones designed by Hodges and Schildhauer with no model to follow, operated continuously for 84 years before the mechanical strut system was finally replaced with hydraulic actuators beginning in 1998. 84 years of daily use, opening and closing for tens of thousands of ships, and the original design held up. The concrete walls poured in 1909 still form the structure of the locks today. The miter gate design, with its self-sealing V and its buoyant hollow construction, remains in use in the original chambers. A major expansion completed in 2016 added a 3rd lane of larger locks to handle the modern container ships that dwarf the vessels of 1914. The new locks use rolling gates instead of miter gates and include water-saving basins to recycle fresh water. But the principle is the same one John Stevens chose over a century ago. You do not dig through the mountain, you float over it. Every year, roughly 14,000 ships pass through the Panama Canal, carrying billions of dollars in cargo between the Atlantic and Pacific. Each one is lifted 85 feet into the sky and set back down on the other side, using nothing but water falling from a lake that was itself created by damming a river that used to flood the jungle every rainy season. No pumps, no fuel-burning engines in the lock machinery, just water and gravity directed through concrete channels and controlled by hollow steel doors that float in their own chambers. The engineers who built it did not have computers. They did not have reinforced steel. They did not even have antibiotics. They had steam shovels, dynamite, concrete, and an idea that most of the world considered impossible. And they carved a passage between two oceans that still works today, more than a century later, exactly as they designed it. If you found this fascinating, hit subscribe and leave a comment telling us which engineering mega project you want to see covered next. And if this video taught you something new, smash the like button so more people can find it.